Okay, so here's an example. We have this circuit. As you can see here, there's this wire that's going left, and there's a resistor, and it's going right. But to connect the two, to complete the circuit, we have a bar that is kind of bridging across. So what this bar is allowed to travel left to right along this path. So the question is, as this thing moves at 2 meters per second, what will be the EMF induced? What's the current and direction of the current? What's the power? What's the force in the bar? And what's the power required to move the bar? So let's start with A. It says, what is the EMF produced? So we saw that EMF is negative N delta flux over delta T. For this one, though, the N is only a single loop. So that's just going to be 1. So we don't even need that. So you just get negative delta flux over delta T. And we saw previously that the equation for flux is just B times the area. And we just keep going. We say, oh, area, this is just a nice little rectangle. So we get delta, and so some length L. And this is some length X from the resistor to the bar, so BLX over delta T. Notice this change of this, but we ask ourselves what's actually changing. The magnetic field is constant in this case, it's 1.2 teslas. L, the width of this circuit, is also constant, 1.0 meters. X is what's changing. So if I rewrite this as negative B L delta X, because delta X is what's changing, we can look at this and we say, what is X over T? X over T is just velocity. So we get negative BLV. If we plug in these numbers, we get negative 1.2 teslas multiplied by 1.0 meters for L and 2.0 meters per second for velocity. We get a value of negative 2.4 volts. And the negative is just there to tell us it's based on the theory. It's saying that it always opposes the change. So the negative says they're opposing the change. Opposing the change in the magnetic field. Current's pretty straightforward. The magnitude of these is just using Ohm's law of V equals IR. We're solving for I though, so V over R. You get negative 2.4 volts over 5.0 ohms equals to negative 0.48 amps. So what's difficult is finding out the direction. Again, it is like a 50-50 guess, but hopefully we can get to the point where we don't need to guess. So let's think about this. There's two ways we can think about it. So if we're using last day stuff, let's think about last day stuff first of all. So we have some magnetic field pointing out of the page. And let's just picture a single positive charge in this rod. Just pretend there's a single positive charge just in that rod. So that's a positive charge. And we know the velocity is to the right. So we can use our right hand rule. So our right hand rule states that if we put our index finger in the direction of the velocity and we point our middle finger in the direction of the magnetic field, so it's going to be out of the page. We don't care about our other two fingers. There's our fingernails, or our pinky and whatever you call that third finger. Where's our thumb? Our thumb is pointing down here. That's our force. This is my right hand, remember. So that tells me that the force is going to be down the bar when this bar moves to the right. So this tells me that I am going to have a clockwise current. So my current is clockwise. So it's 0.48 amps clockwise around the circuit. I can also use flux to solve for this. So if you understand both, you can kind of double check your work. And if we picture, here's my bar, here's my loop. As this bar moves to the right, more and more magnetic field lines are going to be coming through that loop. So if we just picture right now, we count upwards. Above there, we can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 magnetic field lines pointing outwards. Again, it's not exactly 15. This is a representation. of this uniform magnetic field. But if I move this bar a little bit to the right, if the bar was now over here, I can now see there's like 6 more magnetic field lines coming out. It went from 15 to 21. The magnetic field is increasing out of the page. So the magnetic field is getting bigger and bigger and bigger towards us. To oppose that, it's going to create a magnetic field that is into the page to oppose that increase. If I use my right hand rule, my thumb points into this loop, and the rest of my fingers are going to circle around in this clockwise direction. The current is clockwise. For question C, we can use P is equal to I squared R. So just plug in our values. And we get a value for watts, 1.152 watts. For D, says what's the force in the bar. This is, we have this equation in the past day. We can do forces as the current, multiplied by magnetic field, multiplied by length. We get 0.48 amps times our 1.2 Tesla and 1.0 meters. So we get a force of 0.576 newtons. And lastly, for power, power is equal to work over time, which is equal to force times distance over time. D over T is just V, so we get FV. So we have 0.576 newtons multiplied by our 2 meters per second. And we get 1.152 watts, which makes sense. If we're assuming that no energy is lost anytime, power and energy must be conserved. So we have the same values of power, both ways of solving it.